So welcome back. In today's video what we're going to be looking at is just completing the exercises for Lab 9, and then once I've gone through a demonstration of that, I'm going to be looking at the binary search tree. So for Lab 9, what we're going to be doing is we're going to be implementing a binary search algorithm. So let's just take a look at what the binary search algorithm is. Essentially what it is it's a recursive algorithm. So we've looked at recursion before, and it's used for searching an item in a sorted list. Now it can be in any kind of sorted list, but we're going to use an array for our example. It uses the concept of divide and conquer. That just means that, like with most recursive things, algorithms, it's going to try and keep making the problem space smaller and smaller and smaller, and by doing that it's going to get to the solution quicker. You'll see what I mean in a minute once we're going through the example. It'll check the list at half intervals until the item is found or it's defined as not present. That'll make way more sense in a moment. And then in most cases it is going to be faster than a linear search. Not in all cases, depending on the way the data list is sorted, but in most cases it will be. So the binary search algorithm in this implementation is going to be working on an array. And the array needs to be sorted, meaning that this will be my lowest element, and up here we're going to have the highest element, and all other elements are going to be in order. What I'm going to do is define a method, and I'm going to call it find as it was instructed in the lab materials. And this is going to take input of the array. It's going to also have a first index and a last index. These are actually important. These will become important as we work through the recursive nature of this algorithm. But on our first call through, it's simply going to be 0, and it's also going to be whatever our last element is. And finally, we're also going to include a target, and the target is going to be the element that we are searching for in the list. So the first thing we need to do in our algorithm is check that we still have an area to search. This will help define whether we do have an item or whether we don't have an item. How we know we've got an area to search is if our first index happens to be lower than our last index. That means we haven't run out of search area. Then we're going to find the midpoint between these 2 points here. And it is going to use integer division. So the midpoint would actually be 4.5, but that is going to truncate down to 4, and that's going to be our midpoint. Once we've found the midpoint, we want to check if it is the target. And if it is the target, we're going to return the index for that item and say, okay, yep, the item's in here and it is at this index. In our case, that isn't the target because 8 was our target, so that means we're going to be making the recursive call, and we make the recursive call to the left or right. So what we've identified by using the midpoint is we can say, okay, is my target less than the element here? And if it is less, then we're going to make a recursive call to the left. If our target was greater, let's say our target was 43, we'd be making a recursive call to the right. So when we make our recursive call, what we're going to do is we're going to change our indexes. We've checked element 4, so we're just going to keep element 0 as our first index, and we're going to move to element 3, which is going to be our midpoint minus 1, as our last index. Now on this call, the first thing we need to do is check that we've still got a search area, and we know we do because this guy is less than that guy. We're going to find the midpoint. We'll check if that's the target. It's not the target, so this time we're going to make a recursive call to the right. So now we're going to move it up, and we're going to say, okay, this is our first index and this is our last index on this go through. So we check that we still have an area to search, and we do because this guy is still less than that guy. We find the midpoint, and in this case the midpoint is going to be 2. It's going to be the same as our first index. We check that it's a target, and it is, so now this is when we return the index and we say, yep, the guy's in there and he's at index 2. So to implement our binary search algorithm, we're going to be implementing a helper function first, and that's going to be compare. That's essentially just going to take the input of two items and it's going to check their equality. It's returning -1 if the first item is smaller than the second. It's returning 0 if the items are equal, and it's returning 1 if the first item is bigger than the second. For this to work, we're going to have to assume that the item we're using does have the overloaded operators. The final thing to mention here is that it is going to need to work for generic items. So the code for this one is really quite simple. We need it to be generic, so we're just making sure that we're taking in any kind of item. We're calling it compare, and it's going to return an integer. Now, I definitely want it to return an integer, not a size _t, and that's because we are returning -1 here. So now we've got our compare function set up. What we want to do is write the actual function, which is going to implement binary search. So if we have a look, the code again, this is really simple. We've made it generic, so it's going to work for any item. I'm going to have an array of items, and I'm just referencing it, calling it X for now. I'm going to have a target which I'm looking for. I'm also going to have the first item index in that array, and I'm also going to have the last item index in that array. So the first thing we need to do is check if there's still some room to search, or if the item is not in the list. So this is if our first item index is greater than our last item index, we can determine pretty safely that there's no more area to search, and that means the item wasn't in the list, and we're going to return -1. In the other conditions, this is where we work with finding our midpoint. Now that's pretty easy. We're just going to take the first item index, and then we're just going to add the interval of the last item index minus the first item index divided by 2. And that's our integer division there. That's what's going to make sure we're truncating down when we're finding that midpoint. So here we're just using our compare function, and we're just going to check if we have found our target at that midpoint. And if this function returns 0, then we know that the midpoint is the target that we're looking for, and we're going to return that value. If the item wasn't in there, what we're going to do is call compare again. If the target happens to be smaller than the midpoint, so if it returns -1, in this case, we're going to be making a recursive call, and we're making it to the left, which means we retain our first item index, and we're going to be passing in our mid -1. In this case, we're going to be making a recursive call to the right, and to make a recursive call to the right, we retain our last item index, and we're just going to pass in our mid +1 as the first item index. So the final thing I have to do is just test my work. I'm going to test mine by populating arrays of integers. However, I do suggest you might want to test yours with characters and accounts as well, just to be really robust in your testing. So if we look at the code, again, it's a really simple exercise this week. I've just declared an array list. I'm populating it with values. I happen to be making it so that the elements do match the index. So that's going to make it really easy for me for testing, just to see if it is working and if it's correct. I'm going to do get some input from the user, and that's what I'm going to use to try and find in the array. That's going to be my target. I then make a call to that binary search algorithm. If the result is -1, then that means the item was not found in the array, but if the result is not -1, that means the item is stored at whatever that index was in the array. So I'm just going to save that, and then if we just build it, it should be successful. Succeeded. Now, because I've got a simple array, I'm just going to start without debugging for this round through. So let's say I'm looking for the item or the element 4 that is stored at index 4. So that looks like it's working, but shouldn't rely on that. I'm going to test my boundary cases, and I'm also going to do a couple more. So if we do 0, that is stored at 0, so that worked. Let's do, so we're going to do 99. Great, that's stored at 99, so that worked too. Finally, I'm just going to do another case. If we're searching for 101, okay, that element is not in the array.